So Dave Jurowski asked me to introduce today's speaker. Today's speaker is Jim Mayfield from the Johns Hopkins University Applied Physics Lab. He's, I don't know, what do we say about him? He's published widely in areas such as cross-language information retrieval, information extraction, and so on. So without further ado, here's Jim Mayfield. Thank you. David lives far away, and he couldn't get here to introduce me. Okay, so I'm going to talk today about information retrieval. There are going to be two lectures today. I'm going to give the first one, and David is going to give the second one. So I'm going to give you just the real basics of information retrieval, and David will give you some, maybe some more interesting stuff. So what are we going to do? We're going to talk about what is information retrieval. I'm going to talk briefly about evaluation. David might have a little bit more on that, I don't know. Talk about how we characterize documents and queries and how we then compare those characterizations to allow us to score documents against a query. And if we have time, just a little bit on implementation details. So what is information retrieval? The definition we're going to use is it's the automatic identification of those documents that are from a large collection that are relevant to an explicitly stated information need. Okay, so you've got, got a pointer here. You've got a bunch of documents streaming in of all different kinds. You have a user here. There are different levels of relevance. So some documents are very relevant, some are less relevant but still useful. Some are only relevant in the context of other documents, or a duplicate is not relevant if you've already seen it. And so you have a user who has a stated information need. Okay, so that's the environment that we're dealing with information retrieval. There are just a couple of simplifying assumptions that a lot of the research in information retrieval makes. So I just want to talk a little bit about these simplifying assumptions. First, we typically assume that the collection is static. So instead of having a stream of documents coming in, we just have a big static collection. Okay, so we don't have to deal with any dynamicism in the document collection. The second assumption that tends to get made is that a document is either relevant or it's not. Okay, so the documents are relevant independent of any other document, of anything else. You have an information need, and your document is either relevant to it or it's not. Okay, so this idea that we have different levels of relevance goes away. A third very common simplifying assumption is that all documents are exactly the same form. Okay, so they're all text documents. There's nothing else. They're all the same length. And, of course, they are professionally edited. So you can get rid of all that crufty stuff up here. Okay. So that's three assumptions that typically get made in the information retrieval world. And there's one more that gets made. There really is no user. Okay. So this is the environment that a lot of information retrieval research gets done in. You have a document collection. You have some IR system, and what I'm not showing is the information need. You get rid of the user, but you still have a statement of information need. So if you think of in Google, what is the statement of information need? It's the 1.3 words that the person types in to try to get back documents. That's the statement of information need. And our task in sort of basic ad hoc document retrieval is to take this static collection of documents and characterize and index those documents in such a way that you can take the user's information need, characterize it the same way, and then do a comparison that will tell you which documents are relevant and which ones are not. Okay. So the problem as described here is very boiled down from real-world practice, but this is, people make these assumptions just to be able to push the research forward. Okay. I should say that that information retrieval comes out of a different research line than much of the rest of natural language processing and human language technology. It really comes out of library schools where there are people who think a lot about how to do things manually. And has been a strong belief in information retrieval that the hard stuff has to be done manually, and that the purpose of information retrieval is to just sort of automate the very first piece where we're trying to get documents that then a person is going to look at carefully. So unlike something like natural language processing, where from very early on people were looking at semantics and knowledge representation, and only later came to statistical approaches, in information retrieval, it was statistical approaches from the start. Okay, so you're going to see a style of research that is very simple, very statistics-based, doesn't typically have a lot of more deep understanding of the text than just individual words. Okay, so the steps in information retrieval are these. You've got your static document collection. You have to characterize each document in that collection somehow. So you can say, here's the important stuff about this document. You take those characterizations and you put them on disk. Okay? Then a user comes along and says, oh, I have this information need, and states their information need. You take that statement and you characterize it the same way that you characterize the documents that are in the collection. So now you have two characterizations, and now you do some sort of comparison of those characterizations, and you get back a rank-ordered list of documents that the system thinks are relevant to the information need. So we're going to just step through each of these steps to see how it's done. But before that, I just want to talk a little bit about other information retrieval tasks. So the main information retrieval conference is SIG-IR. There are a number of information retrieval evaluations that have been going on for many years. TREC, run by NIST, is the most notable example of that. And so these are things that you will find in the information retrieval literature. What I've described up until now is we typically call ad hoc retrieval. Ad hoc because the user comes along and gives an ad hoc query and you're retrieving it to collection. All these other tasks here are tasks that you'll also find in that information retrieval literature. They include routing and filtering. So in ad hoc retrieval, the documents are fixed and the queries are changing over time, like in Google queries. In routing and filtering, the queries are fixed and the documents are flowing along. You're either trying to say, as a document comes in, oh, that's a good one, or that's a good one, and here's who should see it. Multimedia retrieval. Get this to work a little better. Multimedia retrieval, retrieving things that aren't just text, but also include other things, photographs, speech, and so on. Cross-language retrieval. This is an area where you have documents in one or more languages, and your queries are in a different language. And you want to say, here's my English query. I want to find, say, Arabic documents that are relevant to this English query, so that then I can perhaps hand those to a machine translation system and be able to search over documents in a language that maybe I don't speak. Summarization, trying to, and we've heard about summarization here in a previous lecture. You'll see a lot of summarization work in the information retrieval literature. There's some work in translation. Question answering has been a big topic in information retrieval. The idea is, in addition to finding just that this document is relevant to your need, You want to go in that document and find the exact answer to the question that the person has. So that's sort of been an add-on to ad hoc retrieval. You take a query, you retrieve the document, and you go in the document and pull out the exact answer. Topic detection. When do two stories talk about the same topic? Classification, various kinds of classification tasks that we've seen, or clustering. And novelty detection. When is a new topic coming along? So you've got some stream of documents, news stories say. How do you know when a new story has started? That turned out to be a very difficult problem. Anyway, these are tasks that are part of the information retrieval research community. And for all these tests, if you want to have some confidence that you're doing better, you of course need a way to evaluate what you've done. And for ad hoc retrieval, it's no different. So we'll look a little bit about how these are evaluated. The goal here is to compare two different approaches to see which one is better. Okay? So the goal is not necessarily to say on an absolute scale, how good is this approach? It's just to say, if you have two approaches, which one should be preferred? So you need at least two things to be able to do this. You need an answer key, and you need a way to score a system's result against that answer key to come up with some kind of measure. So this is how it's typically done in information retrieval. And I think in a previous lecture someone mentioned these concepts. But precision and recall are the main measures that are used for ad hoc retrieval. So think of it this way. You've got some collection of documents, an information need. The system looks at that information need and said, here is a set of documents that I think are relevant to that need. Okay? So we got to start thinking not in terms of a ranked list, but in terms of a set. Here is a set of answers that the system thinks is relevant. Okay? Now, from that set, a certain proportion of those are actually going to be relevant. Okay? The proportion that are actually relevant is called the precision. Okay? Also, from that set, you will have gotten a certain percentage of the total ones that are relevant. There may still be some in the collection that you didn't get. The percentage of all the relevant documents that you got is called the recall. Okay? So we have these two measures, precision and recall. And if you look through the literature, you often see statements like, oh, this is a technique that improves precision, or this is a technique that improves recall. Whenever you see a statement like that, you should be very, very leery. And here's why. You really can't judge precision and recall independently. Okay? It's very easy to boost your recall or boost your precision without too much effort. Okay? In fact, you can always come up with a system that gives 100% recall. Take the query, here's your document collection, what do? Return every single document. Okay? Return all the documents, then you've got 100% recall. Okay? To improve precision, you can effectively go towards the other end, return close to 0 documents. Because if your system works at all, the precision at the very early documents should be higher than anywhere else. So if you only return 1 document, you're going to be able to push your precision up. So you can't really talk about precision and recall independently. You have to talk about them together. Okay? So for that reason, in information retrieval, people usually talk about precision recall curves. These are sort of similar to rock curves, but actually these are a little different. So along the... This thing does not want to work. No? There we go. Oh man, maybe the battery's dead. I don't know. Along the x-axis is recall. So remember I said you start thinking about sets, right? And up until now we've just been talking about the set of answers. But these days that's not what's typically done. Typically you get a ranked list of answers, right? So if you take all the documents in the collection and you put them in a list, a ranked list, as you go deeper and deeper in that list, your recall will go up. And eventually you will get to 100% recall. Okay? So that's what the x-axis is. This is looking deeper and deeper into the collection as you're getting more and more recall. Okay? And then precision is, what is your precision over that set of documents? So for the 10% recall position, if that was, say, 60%, that would say once you had retrieved enough documents to have found 10% of all the relevant documents, 6 out of 10 of those would be relevant and 4 out of 10 would not. Okay, so, dang. All right, I'll give up in a minute if this still doesn't work. So we often see curves like this called precision recall curves. Okay, and I think I have an example of an actual precision recall curve on the next slide here. Yeah, so this is an actual set of precision recall curves from Trek 8, which was probably a decade ago. Trek is an evaluation that's been used to try to evaluate retrieval systems. But this just gives you an example of what these curves look like in practice. So here's recall, here's precision. And what we see here is 3 different curves. The bottom line is the median automatic system for that year's Trek. This middle line is the best automatic system at that year's Trek. And this is the best manual run where a person was in the loop trying to do the same task. Okay? So we can see that there's a fairly big difference between these systems in terms of the distance between these curves. A few observations. One, manual processing in this Trek task and the way these tasks work is you get 50 queries that are put together by a retired intelligence analyst. You get a big collection of documents, a gigabyte to a terabyte of documents, mostly news stories. And your system has to return a ranked list of results. And then the analyst who put together the query looks through all the answers and said, yeah, that's relevant, no, yes, no, no, yes, no. Okay? So they actually have people sit down and read the documents and say, is that relevant or not? Okay? And what this says is that even if you put a person in the loop, you're getting nowhere near perfect performance. Perfect performance would be a straight line across the top. It says that every single document that you get back is relevant until you've gotten them all, and then all the remaining documents are there. Okay? So that would be perfect performance. And you can see manual performance is nowhere near it. So we can imagine that this might be a limit to how well automated systems could work. Okay? The second thing we notice is that even the best automated system really has a long way to go before it meets human performance. So there's a lot of room for improvement. And the difference between the best system and the median system, that is also significant. So that there's something that the good systems are doing that the average systems aren't that makes a big difference. Okay. Now, I've lied a little bit here. These are not actually average. These are not individual queries here. These are averaged over many queries. Okay. If you look at a single query, the line is actually going to bounce around a lot. The first document will be relevant, the second one isn't, maybe the third one isn't, the fourth one is. So they bounce around. So these are averaged over many queries. Typically, in Trek, it's about 50 queries. Okay. Another aspect of these curves is that even though these are pretty good summaries of how the systems are doing over 50 queries, it's not enough summarization for some people. A lot of people just want to say, here's my number. Right? I'm getting 83 or I'm getting 26. Okay? So to support people who just want to be able to cite one number, typically what is done is to take the average precision of a curve. And the average precision is simply the area under the curve. Okay, so you take your curve, take the area under the curve, that's your one number. Okay? So the area under these curves would not actually be average precision curves. They would be called what's mean average precision curves because it's the mean of the average precision over 50 queries. Okay, so they call it mean average precision or MAP, which is ambiguous. MAP is also something else, I forget. Anyway, in IR we call it MAP. Okay, so that's how we evaluate these systems and how we compare two systems and how we say, oh yeah, this technique must be better because it's doing better on this kind of task. Any questions on evaluation? Yeah?
Can you go back to the previous slide?
I don't know. We'll see. Yes, I can.
So for an automated system, you can somehow tweak some parameters to control the trade-off between precision and recall and make this curve. But how do you get the whole curve for the human evaluation?
Okay. You're not tweaking to try to trade off precision against recall. The idea is the system returns a ranked list of answers. Okay? Just like Google does, right? You get a ranked list of answers. And to build these curves, you then start looking down that ranked list. Every time you find a relevant document, you calculate what is the precision for that set of documents from there above. Okay? So if the first document is relevant, then say there are 10 relevant documents. Okay? If there are 10 relevant documents, the first one is relevant, then you're going to be at this point in the curve, right? You've got 10% of the relevant documents, and your precision is 100%. You go down, you don't find the next one until the fourth position. Okay? So now you're at 20% recall. Half of them were good, half of them weren't, so you're at that point. Okay? And you can do the same thing with the manual system. And in a manual system, it doesn't mean that a person has ranked list this order. It's just a person has been in the loop and been able to say, oh, add this query term, throw this document out, and so on. So it's a manual assist of a semi-automated system. You get the same ranked list of answers, so you can do the same thing. Other questions? Okay. So what we're going to talk about now is how documents and queries are typically characterized. And then once you've figured out how to characterize them, then we'll look at how documents are typically compared against queries. Okay? So you've got some piece of text. It might be a news article. It might be a tweet. Whatever it is you're trying to be able to search over. You've got this thing. It's got some text. And you need to characterize it. The way that's typically done is you break it into pieces. You fiddle with the pieces. And then you consider those pieces to be your indexing term. You throw them in a big bag. And that is your characterization. Okay. So when I talk about breaking text into pieces, the simplest thing to think of is words. Okay, so you can imagine breaking up some words. And we'll talk about other ways you can do it in a minute. Fiddling with the pieces might be doing something like lemmatizing. Okay. When you throw them into the bag, you lose all your term ordering information. Now, not all systems do this, but it's pretty common. Yeah.
Sorry, what's the second point? Like you said, lemmatizing.
What's the which?
The second point.
Here. Yeah. So once you've broken the things into pieces,
yeah.
Let's say you've just broken up into words by white space. Okay, so everything's delineated by white space as a word. That you might want to use that word. You might not. You might want to lemmatize it. You might want to chop off the s's for plurals. You might want to normalize those words in some way.
Okay.
And there are various ways to normalize, and I'll talk about that.
Okay.
So you've got these pieces. You've normalized them. You've thrown them into a bag, and that's your characterization. Now, you don't have to get these terms out of the text itself. You can also get them from other places. So, for example, you may have some metadata. So, Library of Congress categories or name of the author. You can get references embedded in it, or even text associated with references to it. So if you have a document here and there's a page that points to it, says click here for a taste sensation, you might use taste sensation as words that help characterize that document. So the terms don't have to come out of the document, but typically you do at least take the terms that come out of the document and maybe add some others. Okay, so that's how we characterize documents, and we characterize queries in the same way. So we do exactly the same thing with queries. Okay, and so what we come up with is a characterization, which is just a set of terms that characterizes the document or the query. So what kind of characterization do we do? Well, as I said, the most common thing to do is to just break the text up into words. So if we have a text which is 4-score-and-7 years ago, if we break it up into words, we get 4-score-and-7. Okay. Now there are a couple of processes that tend to get done on these words in information retrieval systems that are called stopping and stemming. Okay. Stopping is simply throwing away words that you don't think are going to be helpful. Okay. And if you have a news collection and one of the words in a document is the, well, the discriminatory power of the is very low because more than 90% of the documents have it. Okay. So typically, people just throw the away. Okay. Even Google, if you look at its default behavior, it throws things like the away. They're actually still there in the index, but you use it. Now, what is the purpose of this? The purpose of throwing the away is not to improve the quality of the search results. It is to improve the speed of the search. Because you can imagine if your search process says, well, find me all the documents that contain each of the query terms, and one of the query terms is the, that says find me all the documents, and you don't want to go through the process of finding all documents that have the unless you can help it. Okay? So this stopping is not something that is designed to improve the quality of search results, even though sometimes you'll see papers that seem to claim that. They're wrong. It doesn't really affect the search at all. It does affect the speed. Stemming, on the other hand, is a technique that is designed to improve the quality of the search. Stemming is poor man's lemmatization. Okay, so typically what you do with a stemmer is you take the words that you got by separating a blank space and you chop the end off. Okay, so 4 wouldn't get messed with. Score, maybe you chop the E off. Why would you do that? Well, maybe you want to match against score, scored, scoring, scores. Maybe you'd like all of those to match. So if you map them all to SCOR, then they'll all match. Okay. 7 year, and so on. Okay. Now, is that a good idea? Well, it depends. Whenever you do any kind of conflation, and stemming is a form of conflation where you're taking more than one term and mapping them all into a single category. Whenever you do that, you have the possibility for 2 kinds of behavior. One is you might be conflating things that you really want to conflate. Okay, if you're looking for documents about juggling, and the document talks about a juggler, you probably want that to match. So if your query is juggling, and juggler matched against juggler, you would like to conflate those two to the same thing. Okay? On the other hand, whenever you conflate stuff, you run the risk of conflating things that should not be conflated. There's a really good example. Something about vegetation. I can't remember. There are 2 words, and you put them together. One of them is vegetation, and should vegetation be mapped to vegetables? Probably not. I'll think of the other word after the lecture. But the idea is if you have this process that takes both vegetation and vegetable and maps them onto the same term, then you're probably conflating things that you didn't want to conflate. Yeah?
For the stop words, I always wonder if we're developing a system ourselves, Should we use the English stop words, or we get our own stop word list from the data collection that we have? Because you know that if we are working on news, probably the word news is going to appear like the word that in each document. So maybe in that case, the word news is going to be a stop word too. So is that a good practice or not?
So the question is, if you're building your own system, should you take a stop list, and the stop list is just the set of words that you're going to stop, that you're going to throw away. Should you build your own stop list based, say, on term frequencies, or should you use an existing one? And the answer is, of course, it depends. It's very simple to use a frequency-based approach to stopping. And if you do that and you take a relatively short list, you're probably okay. If you take a fairly long list, then just because something has a high frequency doesn't mean it's necessarily a bad thing. If you have some computing literature and you're considering the word computer, is that valuable in a collection of computing literature or not? Well, you might think maybe no, but there are certain things like computer engineering where you have a multi-word term that you'd like. Well, you probably don't want to get rid of that, right? So if you have the capability to do phrases in your query, then you got to keep those individual words around.
Can we use document frequency instead of term frequency? Like if the word appeared in all documents, then I'm going to neglect this one.
Yes, you can use document frequency, you can use term frequency. Document frequency is simply the percentage of documents that contain the term. Term frequency is simply the percentage of all tokens in the collection that are the term. And you can use either of those. Document frequency tends to be good for this kind of thing because it almost doesn't matter how frequent a word is in a document from this point of view, because you're simply concerned with what is the discriminatory power of the term. And discriminatory power, since you're retrieving documents, it's can you distinguish good documents from bad? So document frequency is very good for that. On the other hand, there are common sets of stop words that have grown up that tend to be pretty good in most cases. As I say, it is typically not an issue for the quality of the search results. You can stop them or not. It's not going to typically make much difference in terms of the quality of search results. It's simply going to change how fast your system can work. Okay, so you can just adjust it based on how fast you want the results to come in. Okay, so we've got stemming, which is a common thing for folks to do. Now, so this is word-based retrieval, and until recently, most systems worked with word-based retrieval. So they used words or some kind of manipulation of words, stopped words, stemmed words, and so on. And that worked very well for many years. And the problems with it, though, are that it's language specific. So, for example, if you have a stemmer, something that figures out which suffixes to chop off, that's going to be language specific. And while most of the research was in English, it didn't matter. All the tests and conferences and so on were in English. There was a Porter stemmer that everybody used or claimed to use. There were actually a couple, but the one that is still most often cited is the Porter stemmer. In fact, what people call the Porter stemmer is not actually the Porter stemmer. So eventually Porter got fed up and wrote a stemmer that was the Porter stemmer and called it Snowball and said, if you want to talk about a Porter stemmer, talk about Snowball. It's language specific. If you have rules for English, they're not going to apply to Czech or Arabic or anything else. Okay? So every time you want to add a new language, you have to come up with a new stemmer. Word-based systems also perform poorly when the document collection itself is not so nice and clean. So if you have a collection that came from OCR, optical character recognition, you scanned in a bunch of documents and converted them to text. OCR is notorious for making mistakes. And you'll see, if you look in Google Book Search, and you look through how it's translated, what it thinks is in there, it gets it wrong a lot. Okay? Now, in a word-based system, that is horrible because if you make one mistake in a word, its usefulness as an indexing term is gone. Okay? So this is the traditional approach, but there are other approaches. And I'm just going to talk about one other approach, which is called character engram tokenization. So the idea here is that you break your text up, not into words, but into sequences of characters. Now notice I'm talking about character engrams. For those of you from a speech background, when you think engram, you're thinking word engrams, right? In a language model, you might have a 3-gram language model that says you're doing 3 words in a row. This is characters, 3 characters in a row. So if your text is 4-7, the first 5-gram is FOUR blank, the next one is OUR blank S, and so on. And so you might think, what could possibly be good about the term UR blank SC? The semantic content of that has to be so low that it's got to be useless. Okay? Well, it turns out that that's not quite accurate. And this is something that when this kind of tokenization was first introduced, the purpose was not at all to really serve as a replacement for words. It was simply an efficiency hack. Because way back when, back in the 60s, the amount of memory you had in your computer was infinitesimally small. And to have a retrieval system, you really want to have your dictionary in memory. Your dictionary is the set of terms that you have indexed. If you have to go to disk, even to figure out what terms are in your collection, then it's going to be really, really slow. So people back then were very, very concerned with how fast the dictionary was. And they thought, oh, if we use character engrams, we can bound the number of terms that are in our dictionary, because we can just shrink n down until everything fits. So this was originally an efficiency hack. It wasn't until some years later that this guy Mark Damashek said, why don't we use engrams as full-blown indexing terms, and don't just have engrams of 3 for dictionary compactness. Let's grow n to 5 or 6. And there was a big to-do in the literature about this, because Damashek had reported in Science his results and made claims about character engrams and how well they worked, and said that his system was one of the best in the world. And the evaluation was done in Trek, this conference I mentioned, where they have it's a bake-off for retrieval systems. And in fact, his results in Trek were very bad. And so there were letters to the editor saying both he's reporting wrong, that his results were really bad, and this engram idea can never work. Okay? And in fact, the letter to the editor that said this can't work was from Jerry Salton, who was the godfather of information retrieval. And the letters were right that his results were poor. But in addition to using engram tokenization, he also had a novel similarity metric. And his similarity metric was really poor. So it wasn't clear whether it was that it was the engrams that was doing this. But you also had Jerry Salton up saying if you have a document, a query about cart, and you break that into car and art, that just doesn't make any sense, right? What do car and art have to do with cart? Nothing. So this seems kind of counterintuitive, but engrams actually work very well, and there are a couple reasons for that. First of all is volume. So it's like the first change bank, if you've ever seen that little skit. The bank that gives change for $1, you can get 4 quarters, you can get 10 dimes. How do we make any money? Volume. You get much more volume with engrams than you do with words, because not every character in your text begins a word, but every character in your text begins an n-gram. Right? So you have many more n-grams for text than you have words. It is language independent. That is, you can use these sequences of characters no matter what the language is. Right? You just break it up into fixed length chunks of text, and you're good to go. And it is very robust against errors. Okay? So if you have a word, and it's an OCR, and there's an error in the middle of it, it's useless as an indexing term in a word-based system. In an n-gram system, the n-gram before the error and the n-gram after the error are just fine. And so there have been studies done where you take a collection and you synthetically degrade it. 5%, 15%, 10%, 15%, 20% of the characters are changed, deleted, added. When you get up to 20% degradation or 25% degradation, it's almost unintelligible. It's very hard for a person to look at a document that's been degraded 20 or 25% and say it's say what it's talking about. But if you throw those degraded documents into a collection where you know the document is relevant and you do retrieval in an n-gram based system, the first document is the undegraded one, the second one is the 5% degraded, the third one is 10%. It's really uncanny that this approach to tokenization works. And so n-grams are actually a reasonably viable way to tokenize. Now, this is particularly true when you get to non-English languages. So, and there are sort of two ends to that spectrum. On the one side are languages like Chinese. In Chinese, the number of characters is very large, and it's very difficult to tokenize by words because you don't have spaces between the characters. So you don't know where the words are. So a system that is word-based, that's trying to work on Chinese, has to first run a process over the Chinese to break it into words. And that is an errorful process, and it's language-specific and difficult to do. So in an n-gram system, you don't have to do that. If you get just one choice for n in Chinese, you can pick 2. If you get multiple n's, you can do 1 through 3. And if you do that, you will have a pretty good way to tokenize Chinese without having to know anything about where the word boundaries are. Okay. At the other end of the spectrum is a language like German. In German, you're allowed to take 2 words, glom them together to form a word that has never been seen before, will never be seen since, and which is a perfectly legitimate word. And if you can't spot that word, you're going to lose it as a decent indexing term. Okay, so a word-based system has to go through a decompounding process to say, where are the compound words? Let's break them apart. Again, it's an errorful process, and it takes language-specific knowledge to do it. In an n-gram system, you glom these 2 words together. Well, all the n-grams that go across that join, maybe they're no good, but all the n-grams before it and all the n-grams after it are just fine. Okay? So if you look at actual result, here's some results from, again, this is cross-language, no, this is a monolingual multi-language task from Trek from a number of years ago. And these results are precision recall curves like we've seen before. And the blue is n-grams and the pink is words, or whatever those colors are. And you can see that for English, French, and Italian, you get pretty much the same performance whether you use words or, in this case, this is 6 grams. You get pretty much the same performance. Look at German here. This is words. This is unmodified words. This is character n-grams. There's a huge difference here, and that difference comes because you basically get free morphological analysis from n-grams that you don't with words. This is doing the decompounding for you. It's handling other morphological variation because all the morphological variation occurs in some of the n-grams but not others. Okay, and if you look at even more morphologically complex languages, n-grams do correspondingly better. Yeah.
Do you know if these German results are decompounded or are they the full?
No, this is undecompounded German. Yeah. So this is just taking the words straight and. Wish this thing would not do this there. Yeah. Certainly, a decompounded German would be much closer to the top line here, but you sort of get this for free, right? So anyway, as the information retrieval world has opened up to more and more languages, n-grams have gotten a little more currency. They're still not very widely used for a few reasons. One is that because there are more n-grams per document than words, it means that your index size is correspondingly bigger. And that could mean, if you don't do things right, that your retrieval speed is slower. And for web search engines, if you're only going to do one thing, that one thing is speed. Because if you type in a query and you give sort of so-so results, people say, oh, that's so-so, and some will leave and some will stay because they don't want to change their search engine. If you type in a query and you don't have an answer back in a second, people move on immediately to the next search engine. They don't want to wait more than a second. So speed is very important, at least in the web world. So n-grams aren't widely used in the web. The other problem with n-grams is that they don't necessarily play well with other human language technologies that are word-based. So although you can kind of push that, you can actually do things with n-grams pretending they're words, like translation and so on, and get much the same results, even though it sounds wacky. But so the n-grams are a viable tokenization technique, depending on what you're doing. Okay. Once you've picked your indexing terms, then you also need to weight those terms to say how important each term is. If you have a document and you said, oh, juggling is an important term in here, and the is, well, juggling is a term in here, and the is a term in here, you have to give those weights. Maybe the got thrown away, but maybe the document has each, and each was not in your stop list. So the and each, is each a good indexing term? Probably not. Okay? So you would like to give more weight to juggling than you give to each. Okay, so how do you know to give juggling a higher weight? Well, there are a couple of principles that people follow with this. One is that the more often a term occurs in a document, the more likely it is that that term is a good term to characterize that document. So if your term frequency in the document is high, you want your weight to be high. On the other hand, if the term is found in every document, then it's a lousy term. If it's only found in a few documents, then it's probably pretty good. So you want to weight your terms by inverse document frequency. Document frequency, again, is just the percentage of documents that contain the term. So as the document frequency goes up, you want your weight to go down. So the standard basic term weighting in information retrieval is called TF-IDF, term frequency inverse document frequency. So you take the term frequency of the word in the document. This piece is the inverse document frequency. This is the number of documents in the collection. This is the number of documents containing the term. You throw a log on it just for fun. And that is your TF-IDF weighting. So you'll often hear this term TF-IDF. Now, sometimes people will say, I'm using TF-IDF to compare the similarity of a documented query. That makes no sense. TF-IDF is not a similarity comparison. It's a term weight. It just tells you how important is this term in your query. Okay, so we've taken our document, we've broken it into terms, we've weighted those terms perhaps, and not every system uses TF-IDF weighting, but it's very common. Now, and we've done the same thing to the query. Now we're interested in how do we know if this document and this query match? Okay? So for that, we need what's called a retrieval model. And we have 4 basic models that I'm going to cover. And these are probably the most used similarity metrics. There's a whole slew of similarity metrics out in the literature. So this is by no means all of them, but these are the 4 most common kinds of similarity metrics. The Boolean metric, vector comparison, probabilistic retrieval, and the language model. So I'm going to talk about these 4 models. I'll talk a little bit about hybrid retrieval and what's called blind relevance feedback if we have time. Let me see how we're doing here. We're doing okay. Okay, so retrieval models. Way back in the beginnings of information retrieval, as I said, people thought in terms of sets of results, not in terms of ranking. The question was simply, give me the set of documents that are relevant. And so people did what was called Boolean retrieval. In Boolean retrieval, you'd have a query like wild and cats or jaguars and not football. This is to handle if you're interested in jaguars, but you want the animals and not the football team. You would do something like that so that you put wild jaguars and you don't get wild card participation by the. I don't even know where the jaguars are from. So this is a Boolean query, and a query like this, you'd simply say, for each document, does it match this query exactly? Does it have the word wild? If so, continue. If not, throw it away. Does it have either cats or jaguars? If it has one or the other, continue. Otherwise, throw it away. Does it have football? If it does, throw it away. Otherwise, it's in your retrieval set. You get to the end here, and the document is still in the set as part of your set of retrieval results. Okay, so that's Boolean retrieval because it's using Boolean operators to combine the indexing terms that you're looking for. Okay, so originally Boolean retrieval was just a set retrieval. It went blurp and gave you a bunch of documents in no particular order. Okay. Since then, various operators have been added, proximity operators. So is this word near this other word? Wildcard, so does the word match JUGGL something, stemming, and so on. And people have also added document rank to the Boolean model so that you can have this kind of Boolean query and still get ranked results. There's also some use of what we call pseudo-Boolean operators, plus and minus. Plus means this word has to be in the query, minus means this may not be in the query. So the big web search engines will do this. They all default to and these days. That wasn't originally true. When web search first came out, the default was or, and you type in wild jaguars, and you would get all documents that had either wild or jaguars. And Google was the first one that I remember that defaulted to and I think that was a big part of its popularity. Even though you could get the other ones to do and, but you had to do a little more work. There are these pseudo-Boolean operators that you can't combine them with parentheses like you can with the full Boolean operators, but they serve a purpose. So it is from this Boolean kind of system that the idea came along that you could manipulate precision and recall separately. Okay, so in a Boolean system, you're just getting back a set of results. If you do stemming, that is, you conflate words that all begin JUGGL, you are going to increase the number of documents you get back in that set, right? And maybe nothing else is going to change. You might get the same precision, you just get higher recall. It's from this kind of system that the notion that you could manipulate precision recall independently came up. But as soon as you're in the ranking business, if you have a ranked list of results, you have every recall level there. You just have to go deep enough in the rankings. So it no longer makes sense to talk about them independently. The second model that's used was the first one to really give ranked scores out of a comparison. And it's called the vector-based retrieval, or the vector model. And in this model, you imagine that each of your indexing term is a dimension in a high-dimensional vector space. And if that's the case, then a given document or a given query is a point in this vector space, right? If your document has juggling pins, you'd have extent 1 in the juggling dimension, extent 1 in the pins dimension, and so on. So you have this vector space where each dimension is an indexing term. And you can say, okay, I've got say this is my query. Well, let's say this is my query, and this is my document. Okay? If that's the query and then that's the document, sort of the closer those vectors are to each other, the better the match in some sense. So what people do is say, okay, if I want to measure how close these are, well, I don't want to use the length of the vector because that'll just make longer documents look very far away because the vectors might be very long because each word might occur more than once. But really, I want to use the angle between the query vector and the document vector. So if you take the cosine of this angle from the query to the origin to the document, that will be 1 when they are an exact match. It will be 0 when they're entirely orthogonal. Okay, so in this model, you characterize documents and queries in this vector space and simply take the cosine of the angle. Okay, this combined with TF-IDF weighting is probably the best known retrieval model. And it's been used very successfully in a variety of systems. Let's move on. There are 2 more models we're going to cover. One is called the probabilistic model. And there are really 2 important things about the probabilistic model. One is an articulation of what it means to rank results well. This was called the probability ranking principle. It was stated by Robertson in this paper here. And it says that optimal retrieval performance is achieved when documents are ranked according to their probability of being judged relevant. It sort of makes sense, but this was sort of the first explicit articulation of that point of view. Okay, so there's this probability ranking principle, which actually, people will come along and challenge this and say, no, that's not how we should do ranking. We should do it some other way. In probabilistic systems, you'll often see them using odds rather than direct probabilities. The other important thing about probabilistic systems is that there was a lot of study of term weighting, and new term weighting mechanisms beyond TF-IDF were developed. Okay? This is probably the most famous. This is Okapi BM25 term weighting. And this is not a similarity metric. This is a term weighting, like TF-IDF. But it tends to give much better results than TF-IDF. So it has a term frequency component. It has a document frequency. It has a term frequency component right here. It has a document frequency component here. And it also has document length normalization stuffed into it here. Because when your documents are widely different lengths, simple TF-IDF weighting doesn't tend to be optimal. So this is a very common weighting scheme that's now used. That you'll see a lot of reports reported using this metric. Okay. The final similarity metric we'll talk about here is will be very familiar to some of you. It's the language modeling approach. And in the language modeling approach, we ask the question, if we build a language model from this document, what are the chances that that language model will generate our query? Okay. So, what is a language model? A language model is simply a process that outputs string in a language. So here we have a language model. It says 10% of the time put out the, 20% purple, 20% green, and 50% frog. So green the frog, green, purple would be a string in this language, and we could calculate the probability of that string coming out just by this unigram model. Okay, and when it comes to language models used for information retrieval, unigram models are by far the most commonly used. There has not been shown to be a huge boost to be gained by going to higher order n-gram models. For each document, you build a language model, and you do that basically by saying, okay, if this is a document, let's say it's going to generate terms just according to the percentage of the time that term occurs in the document. So you're basically generating according to the maximum likelihood estimate based on the counts in that document. So you do something like this. You say, okay, the probability that the language model from the document would produce the query is simply the product of the probabilities, that each individual term would be produced. Okay, and you can take the maximum likelihood estimate here to give you those probabilities. Okay, now if you do this, your results will be horrible. Why? Say you have a long query.
So if the document didn't contain one of the words.
Exactly. If you're missing one of the words, then one of these probabilities is 0, and the whole thing goes to 0. Okay? So just like in language models for speech and so on, you need to smooth this model so that you don't have the 0 probabilities. You'd like to assign a small probability to every word, even if it didn't occur in the document. So what people do is they smooth by taking an entire collection. So if you take your whole collection and you look at the probability that a language model based on the whole collection would generate the query, and you combine that with the probability that the document itself would generate the query. And basically this is just, the most common way is just to do linear interpolation. This is also called Jelinek-Mercer smoothing. You just take for a given term, you say, well, what's the frequency in the document? What's the frequency in the collection? You have a linear combination of those two. Okay. So since the documents are typically much shorter, the probabilities coming out of the documents tend to be much higher relative to the probability from the collection as a whole. So if a term is not in the document, you still get a small boost from the collection, but it's not so huge that you're overwhelming the other terms in the query. With this kind of approach, you don't really need to do term weighting. Term weighting sort of falls out of the fact that you're calculating these probabilities from the document and the collection. Okay. So those are probably the 4 most commonly used similarity metrics. And so now you probably know enough to go out and read any ad hoc IR paper and have some clue what they're talking about. Any questions on any of these similarity metrics? Okay. So I'm going to cover just a few more topics here. We have about 15 minutes left. I think I'm going to skip this. I want to talk about something that's called blind relevance feedback. This is a technique that's often used to boost retrieval performance, meaning the quality of retrieval results. There's a technique called relevance feedback. In relevance feedback, you have a person who is doing the retrieval. And the person types in their query, and they get back a list of documents, and they say, oh, my query was about cars, and I got this document back, and I saw in this document the word automobile. And I'd forgotten to put that in my query. But now I just realized if I'm asking about cars, I probably ought to ask about automobiles too. So I will take automobile and add it to my query. That's called relevance feedback. Okay, you're finding more relevant terms based on your retrieval results, and you add them back into your query. Blind relevance feedback is doing that without actually having the user there. Remember, we've thrown away the user, so we have no user. In blind relevance feedback, you do a retrieval, you take the top documents, and you pull important terms out of those top documents and add them to your query. Okay? And that simulates this relevance feedback task. Now, you don't know that the terms you pulled out of these top documents are actually relevant to the query. But if you did a good job in the first retrieval, they probably are, and so you're adding good relevant terms to your query. And so this bears this out. Here's a typical blind relevance feedback study. This blue line and or purple line down here is what you get without doing this technique. If you do the retrieval, take the top documents, use your favorite method for pulling out good terms, maybe point-wise mutual information or dice statistic or something, to pull important terms out of those top documents, add them back into the query, and you get this huge boost in performance. Okay, so this is, so here we have almost a 28% increase in mean average precision by doing this. So you will see many, many systems do this. The web search engines don't typically do it because it's a two-step retrieval. You have to do two retrievals, and the second retrieval has many more indexing terms, query terms, so it's slower. So you don't typically see this in a web search engine, but many systems that work on smaller collections will do this. And I don't know if I have a. See if I'm. Yeah. I don't have a slide on this, but if you look at what this is doing, it is taking the queries that you're doing well on and making you do really, really well on them. And it takes the queries that you don't do well on them and drives them into the dirt. Okay? If you have a query that you're doing well on, it means the top documents are relevant, there are good terms in there, you add them to the query. If there's a query that you're not doing so well on, maybe there's only one or two relevant documents in the top set, well, you get words out of those relevant documents, and you get words out of all the other documents that are not relevant. And you add them to your query, and it really kills the query. So you always have to be careful, no matter what your task is, information retrieval or anything else. Ad hoc retrieval. In ad hoc retrieval, you see this, you think, golly, that's great. But it's only great for a certain subclass of the queries. If you don't look query by query, you're going to miss this. And it depends on what your goal is. If your goal is to do really well in some queries, this is great. If your goal is to bring up the floor in all queries, then you probably don't want to do this. It's going to kill you. Okay. So that's a technique that's often used. I'm going to finish up here, probably. I might do one other topic, but with just a couple words on implementation. The way that IR systems typically work is by building an index of the query terms. So this index is like a concordance. That is, you take all your collections and you find all the terms that occur in them. So they're here. So these are all the terms in our collection. And you put them in order some way that makes it easy for you to find them. Okay? So here's our collection. It has alfalfa, angst, and so on. And then for each word, you build a list of all the documents that contain that word. And you put that list also on disk. This is usually called the postings file. So if you hear about the postings file, it's simply a large file, typically on disk, that says it's basically the partition of, well, it's not a partition of documents. It's the list of all, for any term, list of all documents that contain that term. Okay. So at retrieval time then, you take your query, you break it into terms, you go into your index here, and my query is alfalfa arbuthnot. So you go to alfalfa, you say, oh, here are all the documents that contain alfalfa. And here are all the documents that contain arbuthnot. And now you have a list of documents that contain one or more terms. And now you do your similarity comparison only on those documents. Okay? And in fact, typically, if you want to improve your performance, you will order the query terms in such a way that you'll do the least frequent first, so that you start to build a collection of documents that that have maybe arbuthnot as the least frequent term, and then you add alfalfa and so on. So that by the time you see the very common words, you only update your similarity metric for the documents you're already tracking. Okay, if there's a very common word in the query, each, and you have other words, juggling and alfalfa, then you don't want to probably bring in documents that just have each. So by the time you get through juggling and alfalfa, you have a set of documents, and then you modify the scores for those documents based on each, but you don't add any new documents. Okay. So this is called an inverted index. It's the most common data structure that is used. This dictionary is usually these days held in memory. It used to be in the old days that that part of this that you tried to hold the words in memory, but the actual pointers would be on disk as well. But this thing is typically held in memory now. This is typically on the disk. So that means that for each term in your query, you have to do a disk seek. That means that if you have a shorter query, the performance is going to be better. And that's one of the reasons that that there has been no drive to try to get users to increase the specificity of their queries over the average of 1 or 2 words that they usually give. Because if you encourage users to add more terms, which would make their query more specific, you also add a disk seek for each one of those terms, and that slows you down. So, so this is the most common data structure for retrieval. There are other data structures you can use, signature files, which is basically a hashing technique, pat trees, and so on. But this is the most common. It's also very common to compress these data structures. So if you just take a large data collection and do it just like this, you're going to have very large data structures. So what people do, for example, take this dictionary and compress it by saying, okay, instead of storing each one of these words, and I don't have a good example here, but if we had alfalfa and Alfredo, you would store the whole string alfalfa. But then you wouldn't store all of Alfredo. You wouldn't store the ALF. You just have a number 3 and then REDO to say that, oh, it's just like the word before me except for the first 3 characters, and then we've got these other characters. That's an example of the kind of compression you can use. And there's a pretty good book called Managing Gigabytes that will go into infinite detail about different compression methods that you can use to reduce the size of your index. And reducing the size of the index is not simply a matter for disk space. It is a speed issue as well, because when you have the compressed index, the transfer time from disk is smaller, and the disk costs overwhelmingly control the cost of retrieval. So if you're only if you're going to alfalfa and you're getting this document list, if you're only pulling in half the bytes to get that list of documents, you've saved half the transfer time for the query. Okay, so that's. I think I will probably not go on there. Let me just summarize what we've learned. So information retrieval, it's the automatic identification of documents that are relevant to an explicitly stated information need. This is our substitute for the user, right? We don't have a user. The user has said, here's an information need. They've written it in language, and that's what we're going for. There are a wide variety of problems that typically go under this information retrieval rubric. But the fundamental issue that is common to many of them is this ad hoc retrieval, matching a query to a document. Precision and recall are the most commonly used evaluation metrics, often combined into a single number, which combines the precision and recall by taking the area under the curve and averaging that over many queries. So that's where you get this mean average precision. documents and queries are typically characterized by some kind of indexing term, often words or some variant of words, but increasingly frequently these days, character n-grams. There are a number of similarity metrics that you can use to compare a document against a query, and we looked at 4 of those. Blind relevance feedback is a technique that's often used to boost performance on the already reasonably performing queries. And because collections are large, you really need to take care when you're figuring out how to store this information on disk. Okay, so I think I will stop here and take any questions you might have. What's going to happen next is, after the break, Dave Urowski is going to go into more detail on some of the more interesting subproblems in information retrieval. So any questions on any of these topics? Oh, by the way, if you would rather ignore the questions and do a puzzle, this is each letter represents a digit. They're all distinct, and you have to map those to the digits 0 through 9. Okay, so any questions? Yes?
Can you go back to the inverted index?
Yeah, sure.
I wanted to make sure I understood it.
Sure.
So the number, that like for alfalfa 2, that's saying go to the pointer, and then
There are 2 documents there that, yeah, right.
And,
So,
then the other, on the posting side, is that the term frequency of that term in that document? Or
Yes,
is it-
yes. Now, so this is the most simple variation. There are other variations you can use to get more information. For example, if you want to, if you wanted to do phrases, then, well, there are different variants. The most obvious variant is to say, well, in addition to which documents do the words occur in, where'd it go? In addition to the fact that it's in these documents, you would say, what position within these documents do they occur? If you had the position information, then when you retrieve, if you're looking for the phrase alfalfa arbuthnot, then you can say, oh, it's in this document, it's at the alfalfa's at this position, arbuthnot is right after it, but in this one they're completely separate. So you would add, these can be augmented to have further information, but that's the basics. Other questions? Okay. Well, thank you, and David will be here in a few minutes, we hope.